All right, today we're going to demystify one of the most powerful and honestly, one of the most beautiful ideas in all of mathematics, the definite integral. We're going to see how it solves a problem that had some of the greatest minds stumped for centuries. Okay, let's get into it.
So, let's start with a simple question. How do you find the area of a shape when its edges aren't nice, neat, straight lines? Think about the space under a rolling hill or the area of a lake with a curvy shoreline. Your basic geometry formulas, they just don't work here. For literally thousands of years, we've had formulas for shapes with straight edges, squares, rectangles, triangles, all that good stuff. But the second you throw a curve into the mix, bam, everything changes. All those trusty formulas you learned in school, they're suddenly useless. And that leads to a really fascinating question. How in the world do you measure something that's constantly changing?
So let's really dig into that challenge. For centuries, this was a massive roadblock for mathematicians and scientists. It was simply the problem with curves.
And I'm not kidding, this isn't just some textbook exercise. For the longest time, there was just no perfect way to calculate the area of these irregular, curvy shapes. It was a genuine, massive mathematical hurdle. So, when you can't get a perfect answer right away, what do? Well, you approximate. The big idea here was to tackle the tricky curve by using something simple that we can measure easily, the humble rectangle. The thinking was, if we could just slice up the space under the curve into a bunch of rectangular blocks, we could at least get a rough estimate of the area. And that simple idea of approximating, well, it leads us to an absolutely brilliant strategy, which I like to call the infinite slices method. Now, if you use just a few big, chunky rectangles, you get a starting point, but it's pretty obvious that the approximation is flawed. You can see all those gaps where we've missed some area, and you can see the corners that stick out where we've added too much. It's just not a perfect fit, not even close. But here's where the magic starts to happen. What if we use more rectangles and we make each one a lot thinner? All of a sudden, those gaps and overlaps, they start to shrink. The more rectangles we squeeze in there, the more accurate our approximation gets. We're getting closer and closer to the true area. Okay, this is the mind-bending leap of logic. I need you to go with me on this. Forget 100 rectangles, forget 1,000, forget even 1,000,000. What if we could use an infinite number of them? Each one would have to be impossibly, infinitely thin, but if you could lay them all side by side, together, they would fit the curve perfectly. No gaps, no overlaps. It would be a perfect match. Now, obviously, we can't actually sit here and add up an infinite number of things. I mean, that's impossible, right? Well, this is where calculus comes in and gives us this just astonishingly elegant shortcut.
And this is it, the definite integral. That formula looks a little intense, but the idea is pure genius. It connects our area problem to a totally different part of calculus called derivatives. It turns out that the process of adding up all those infinite slices is perfectly reversed by finding something called an antiderivative. Think of it this way. To find the total area under a curve from point A to point B, we find this special accumulation function, let's call it a capital F, and we just subtract its value at the start from its value at the end. That's it, f of b minus f of a. So how does it actually work in practice? Well, it's a pretty straightforward four-step recipe. First, you take your curve's function and you find its antiderivative. Then, you plug your endpoint, b, into that new function. Next, you do the exact same thing for your starting point, a. And the final step is just simple subtraction. The value you got for b minus the value you got for a. And that gives you the exact area. And the result you get is just stunningly precise. For that area under the simple curve y equals x squared, between 1 and 3, the answer isn't about 8 or somewhere close to 9. No way. It's exactly 26 divided by 3. This is the incredible power of calculus. It replaces a fuzzy, messy approximation with perfect, beautiful precision. And what makes this tool even more useful is how flexible it is. It follows a few simple, really intuitive rules that let us play around with it in some clever ways. We're just going to look at two of the most fundamental properties right now. What happens when you split the area into pieces, and what happens when you decide to integrate backwards? This first property is really just common sense. If you want to find the area of a long hallway, you could measure the first half, then measure the second half, and just add them together, right? It works the exact same way here. The total area from A to B is just the area from A to some middle point C, plus the area from that point C onto B. Simple as that. This second rule is also pretty neat. If integrating from left to right, from A to B, gives you a positive area, then what happens when you go the other way, from B back to A? Well, you get the exact same number, it just becomes negative. It's like you're reversing the direction of your measurement. Okay, now that we have the basics down, let's look at a slightly more complex and way more practical application of this amazing tool. So far, we've just looked at the area under a single curve. But what if you need to find the area that's literally trapped between two different curves? Imagine the weird lens-shaped space between two overlapping parabolas. Now, this might seem a lot harder, but with integrals, it's surprisingly easy. And here's the formula for it. To find that area that's trapped between them, you just integrate the difference between the two functions. You literally take the top curve's function, subtract the bottom curve's function, and integrate that new result from your starting point A to your endpoint B. It's that simple. And this right here is probably the most important takeaway of the whole explainer. The definite integral is so much more than just a clever way to find the area of weird shapes. The core idea, breaking a complex problem into infinite small pieces and then summing them up, is a cornerstone of modern science and engineering. It's used to calculate how far a rocket has traveled just from its velocity. It's used to find the volumes of complex 3D objects. It's used to model everything from financial markets to the flow of electricity to creating the graphics in the video games you play. It's everywhere. So that leaves us with one final question. This method of thinking, breaking down a huge, messy, seemingly impossible problem into infinite, manageable slices, is one of the most powerful problem-solving techniques ever invented. So think about it. What complex problem in your world, in your work, or in your life could become a whole lot simpler if you could just break it down into infinite tiny pieces?